So hello everyone, my name is Crystal and I'll be presenting with my colleague Mitko. We are both senior engineers at VMware Carbon Black. We're part of the security business unit and located in Sofia, Bulgaria. So as you can see from the title of our presentation, we'll be talking about building high volume throughput systems and more specifically, high volume data ingestion. Our plan is to take you on a journey, starting from the most simple ingestion system anyone can imagine, and end up with a distributed ingestion platform capable of processing millions of events per second. So, quick disclaimer, I'm sure you've all seen that if you've watched other VMware Explore presentations, but I'll give you a second to read through it. So, just to give you a glimpse of the scale of our product so that you know we're talking from experience, we are currently processing 1.4 million events every second at a rate of approximately 6 gigabytes per second. Our EC2 fleet consists of more or less 3,000 machines running more than 17,000 containers. That's 60,000 virtual CPUs, 350 terabytes of RAM, and around 7 petabytes of storage. At this point, you might be wondering what exactly are we building, and the simple answer is that this whole infrastructure is powering a gigantic search engine used for an activity known in the cybersecurity domain as threat hunting. That is, we collect everything that's happening on your machine and make it searchable. Then, security analysts are proactively digging into this plethora of data, trying to detect and isolate advanced threats that evade existing security solutions. So to make this clear, we're not building an ordinary antivirus software. We're building a data platform that enables security specialists to track down vulnerabilities, to investigate, to learn how novel attacking approaches work, and so on. Okay, so let's see how we can build such a system from scratch. We'll start really basic and discuss the problems and solutions of the proposed architectures as our architecture evolves. In the beginning, I will start by describing the thought process behind building a generic ingestion stream. And later on, my colleague Mitko will continue expanding on that by taking our own architecture as an example. So, as I said, starting really simple. Let's say we only have one service and our clients communicate directly with it using HTTP. See? Simple, a great beginning. This will most likely work, but it has some major problems. One of them is related to scalability. As the number of clients increase, the demand on the single service will increase proportionally until it can handle all incoming requests. Then it will most likely crash, which in turn will lead to downtime. And that's really the second major problem here. Lack of availability due to this service being a single point of failure. So one way to alleviate the scalability problem is to scale the service vertically. That is, in a sense, buying a more expensive machine with more RAM, CPU, I/O, disk, etc. This approach can work as a short-term solution, and actually it is quite often employed as a first step when scalability issues arise in order to buy some time for the developers to come up with and implement a better solution. Though, as I said, it's only a short-term solution as you can't scale vertically infinitely. As you try to scale further and further, the hardware becomes increasingly more expensive. And also, what's even more important in our case is that vertical scaling doesn't solve the availability issue. It doesn't really matter how powerful your machine is. The probability of something happening to it is exactly the same. So a better solution might be horizontal scaling. That is, having multiple copies of our service running simultaneously while splitting the traffic between all of them. The cost of adding resources this way is much lower since we won't need state-of-the-art hardware anymore. But quite the opposite, we can run our services on more affordable infrastructure. Also, a huge advantage is that we can theoretically run as many services as we need. There is no physical limitation that prevents us from scaling further at any point. The availability issue is also alleviated to a huge extent. If any of the instances fails due to some random reason, others can continue processing client requests. That is, of course, assuming that the load balancer is properly configured, which is one of the challenges when it comes to horizontal scaling. But let's leave this topic for another time. So now, even though we have achieved horizontal scalability, there are still several issues which are holding us back from processing millions of events. More notably, such an architecture is well suited to handle gradual increases in traffic over time, but what happens with sudden traffic spikes? What happens when it hits 8 a.m. in the morning and the traffic increases tenfold, for example? We can't expect to scale this fast, really. Our services will be overloaded with requests effectively DDoSing them, and our service will become unavailable. One potential solution is to add rate limiting to the load balancer, which will prevent the servers from getting overloaded. But actually, from user standpoint, the outcome will be identical. It will appear as the service is not really functioning. Another approach is to pre-scale our service ahead of time, essentially increasing the number of servers before expected traffic spikes. This can really work sometimes in certain scenarios, like, for example, on Christmas, if you know that you will be hit by much higher traffic than expected. But then what about unexpected situations? And what about the cost? Pre-scaling means you will have to pay for something you don't really need right now. And on top of that, it also requires manual intervention. So a more sustainable solution would be to somehow offload the excessive requests in a way, saving them for later, and then processing them once our instances have enough capacity. In other words, we're migrating from push model, where clients are constantly pushing information to our servers, to pull model, where our servers are pulling from a backlog of requests whenever they can. In such a model, you can't really overload the servers, since they will be configured to never take more than they can process. In case the backlog gets too big, we can always add more servers to start burning through it faster. So, as you can see on the chart, the load balancer doesn't communicate directly with the service anymore. Instead, it talks to a persister, which job is very simple. It receives a request, writes it to a persistent storage, and returns 200. The 200, however, now has a slightly different semantic. It doesn't mean your request is successfully processed, but rather suggests something like, we confirm we received your request and we'll process it eventually. On the other hand, our service, now called the processor, runs in an infinite loop, and every once in a while, when done with its previous job, asks the persister for a new one. This cycle continues indefinitely and is much more stable than simply having our service behind the load balancer. In this model, we can even tolerate, if you think about it, 100% of the instances of our service going down, as long as the persister is writing down all requests to a non-volatile storage. At this point, you might be asking yourself, so what's the difference between having our service versus the persister right after the load balancer? Why can't our service react to sudden traffic spikes, but the persister can? And that's really an excellent question. The difference really is that the job of the persister is really simple, and also it's highly specialized for this kind of job. The persister instances are hosted on a machine with huge network bandwidth and fast NVMe storage. Their single job is to write to an append-only log and to keep a pointer indicating until where this log has been processed. Such a service can handle thousands of requests per second without budging, while our processor is much more inefficient in this particular job. And on top of that, it has to actually process the incoming requests, which, depending on the workload, ends up consuming most of the available resources. So now, We have a pretty solid, eventually consistent system, but the persister still has some flaws. It is writing to a centralized location, which means it needs to log the append only one. With enough instances writing to this same location, this will certainly become a bottleneck in no time. Also, what happens in case our non-volatile storage gets corrupted? We will lose all our saved requests and thus violate our 200 stateless request contract. A potential solution would be to partition the incoming requests among a number of storages. In other words, have multiple non-volatile storages, and when persisting the request, pick one of them based on some of the request attributes. This will fix the bottleneck we have introduced using a single storage, but is still vulnerable to random hardware failures. If one of the partitions go down, we'll lose some percentage of the requests, and we don't really want this to happen. This we need to not only partition the data, but to also replicate it. That is, each of our partitions needs to have 2 or more replicas which are storing exactly the same data so that they can take over in case something happens to the main one. The problem with this, as you might have started noticing, is that it's starting to get increasingly complex, and we're not even dealing with business functionality here. We're dealing with some auxiliary functionality. Configuring partitioning with replication requires a lot of specialized knowledge and expertise. It's not something we would want to support on a daily basis. It would be great if we can utilize maybe some third-party solution that's providing us with this functionality out of the box. Luckily, if you take a look at the persister, it looks awfully like a message broker. And there's a plethora of mature message broker solutions out there to choose from. One possibility would be to maybe pick a queuing service like SQS if you want something fully managed, or let's say Redis if you want to deploy this on a proprietary infrastructure. Another solution would be to use a streaming service like AWS Kinesis or Kafka, respectively. Streaming and queuing, although really similar, provide different semantics and guarantees. Deciding which one to choose is heavily specific on the use case. So, do you have multiple consumers? Do you need to process the requests in the same order in which they arrived? Do you need to peek back in time and process some of the requests again? There are a lot of questions that need to be answered before choosing the right tool for the job. And in our team, we have concluded that AWS Kinesis is really what we're searching for. After introducing Kinesis, the diagram becomes much simpler. We don't have to manage high availability data stores, deal with partitioning, supporting custom code for keeping track of progress, etc. Kinesis does everything for us and much more. It supports encryption, multiple clients, custom data retention periods, and most importantly, it scales extremely well. Just to give you an idea of our scale, currently we have a Kinesis stream with 30-something thousand charts, capable of ingesting gigabytes of data and tens of millions of records every second. So, to recap, what's our generic ingestion architecture by this point? Clients are sending data. The load balancer splits the requests among our persister instances, which are only acting as proxies, and we're writing everything down to our Kinesis stream. From there, our main service, the processor, is pulling data from the stream and processing it as it has the resources to do so. In case the system detects that the processor is falling behind from processing the latest messages, it immediately starts a bunch of new instances to deal with the load. At this point, we have a system capable of ingesting millions of messages, but what exactly does it mean to process it? That's really the part where the architecture becomes business specific and we can no longer look at it in a generic way. That's why I will give the word to my colleague Mitko, who will take a deeper dive into some of the specifics of the architecture of the threat hunting solution we're building. Thank you.
Thank you, Stu. So Up until now, we have employed some best practices for achieving high throughput in our ingestion platform. Further design decisions are usually case by case and are very business specific. So now we have a stream between the persistor and processor. Let's put some more specific context to the diagram. We will explore the use case of the Threat Hunter project of Carbon Black. Threat Hunter receives security events from all devices, indexes the data, and makes it searchable. The search is intended for security experts and analysts who need a comprehensive view of what is going on in their organization or to chase down a specific incident. We'll take a very simplified version of Threat Hunter use case, and we divide the data in basically two types. It's ingesting the data that's above the dotted line and searching data below the dotted line. So on the ingestion side, we have devices sending security events to the persistor. The persistor augments the data and pushes it to a Kinesis stream for indexing. Next, the indexer component reads from the shards of the stream, builds indexes, and stores them on a data storage like S3. And since indexes are already handled by the indexer component, when a user does a search, we directly contact all indexes and execute the search query. In this scenario, indexers should be right-sized to accommodate read and write operations. So that would be a problem. Now, what if an ingestion and search load are very different? We need to somehow be able to scale both functionality separately to meet the SLAs of the Threat Hunter service. Now, the solution of that would be to would be in the spirit of microservices, and it would be to split read from write actions. We let indexers just build indexes, and therefore we introduce a searcher component for reading the data. So when an index is finalized by an indexer, meaning it is complete, it is then persisted to the index storage. From there, it is being taken by a searcher and is being made available for searching. And now we can do all kind of read and write optimizations without any concerns of hitting the performance of one service or the other. We can also scale both components independently. Now all of our three components have a single responsibility. We can squeeze some more throughput by using the right hardware for the different types of tasks to perform better. Like the persist maps events and pushes data to Kinesis, to the stream, so it needs a lot of CPU and network bandwidth. The indexer constantly indexes data and offloads those indexes to the storage, so it needs, again, CPU, memory, and again, network bandwidth. The searcher, on the other hand, needs to pull an index from the storage only once, and then it hosts it permanently. That means more memory and a fast disk for that component. So knowing what the applications are doing is critical for provisioning machines with the right resources. The next problem we have with this approach is that data in our indexes is mixed. We would like the data of one customer to be separated from data of other customers. So the obvious solution here would be that we need to partition data. Data partitioning has many benefits, like improving concurrent access, isolation, resilience, and so on. But we still have to decide how and where to do the partitioning. For example, we can make the indexer read mixed data and partition it internally in the indexer, meaning each indexer instance will have to build many indexes for different for different customers in parallel. So going down that path, we'll have to deal with many edge cases, like when it needs to start building yet another new index, but there is no more capacity. Should it then drop the data or leave it for later? None of the options are really acceptable. Therefore, we tend to partition data upstream, so preferably as early as possible. In our case, we use the customer ID as a partition key, so we will let partition data for each customer separately, and let Kinesis do the actual partitioning, because that comes out of the box for us. and we have to do it specifically. All we have to do is to specify on what fields to be aggregated on. So now, as you see on the diagram, each shard has ordered data from just one customer, and each index which the indexer reading the shard produces will have data again for just one customer. And we also save some partitioning computation costs in comparison if we do it in the indexer. We have achieved a similar behavior previously by building our own partitioning solution, but with the help of a well-proven product like Kinesis, we don't need to deal with all the implementation challenges that comes with data partitioning. All right, but even so, the search experience is still poor because of searches taking too much time to complete. Searchers are hosting indexes with data of only one customer, but a single search has to hit, of course, all of the searchers to find all the matching results. But we have introduced data partitioning. So every index belongs to exactly one customer. In our business case, and because of data separation, it is logical that a customer is able to search data that belongs only to the same customer. That's our business requirement. We can make use of that fact, and when a search is triggered, then we actually need to contact only the relevant searchers and execute the search query only on them, right? But how do we know which ones are the relevant? We need to somehow keep track of the indexes. So we'll store the customer and host location of all the indexes, so we can easily retrieve all the indexes for a given customer in case we need to. We again face here the decision, that's an important one, of picking the right tool for the job. For our purpose, a suitable choice would be a key value store over other database types, because that is the nature of the data we want to persist, and because we do not need transactionality when writing records. That registry of indexes alone won't do the trick. We also introduce another component here that retrieves the relevant searchers from the registry. So it retrieves their locations, contacts the searchers, and collects all the results to serve them back to the customer. We call that component the search API. So let's assume as soon as an index is ready and available on the index storage, the indexer component adds a record to that registry about the finalized index. And at the next moment, a search is triggered, which should include that index. But that index is not yet hosted and cannot be contacted, and the search will most probably fail or timeout. We can solve that many ways. One of them is to synchronize the adding of a record to hosting the index. So we synchronize both writing to the registry and hosting the index. But that will require a lot of effort to do a cross-component sync of different actions, and that for sure will block execution on one side or the other. This is where we need to embrace eventual consistency. That's a very important concept in high-throughput systems. So we'll take the other approach where searchers add records to the registry when an index is already hosted, and thus ensuring any index on the registry is accessible. Our data will eventually be searchable after it is indexed. We have improved our search performance in a way, but we still notice a problem with the ingestion. Indexers are not equally loaded, and some of them fall behind on processing records. Records on a stream on different shards have latency, and we go above the accepted thresholds. That is because different customers send very different data volumes, and after partitioning, we end up with a very different amounts of data on each shard. So on the diagram, there you see different arrows showing the different shards, and each digit on a stream represents a message, and the value of that digit represents its belonging to a different customer. So we have to find a way to somehow balance that data volume on individual shards. That will result in a more equalized CPU and memory usage of the indexer instances that will allow us to scale horizontally much better. If we assign, let's say, the hot shard to multiple indexers, that will result in data duplication and inconsistency, and that's not what we want. So we need to split shards. That action is supported by Kinesis, but in our use case, we have to preserve data partitioning because that is also a fundamental requirement in our architecture. And actually, we don't need to split all the shards. We'd like to split only the hot shards. Here's where the need to alter the default stream behavior with some custom logic. So we create a side module. We call it the stream manager to split and merge shards for us as data volume fluctuates. The stream manager has to know about data volumes as it is supposed to react on volume changes and take appropriate actions of splitting or merging. It would be practical for the manager, it wouldn't be practical for the manager to reread the whole stream. So we also already have a component that processes all the data prior to the stream. We take the decision to enhance the persister to store aggregated telemetry data of the data volume, as this introduces a very small overhead in the persister processing, but we gain on the other side an important insight on data volumes. And the telemetry data needs to be stored somewhere as well. We choose to use a time series store as it is most suitable for telemetry and metrics use case. So our stream manager queries the telemetry store to decide which shards to split or merge to achieve approximately equal load on shards. Having this in place, we can use a simple CPU-based horizontal scaling policy for the indexer, because the volume on the shards will be relatively equal. What we did here is, instead of controlling how much data each indexer picks, we control how much data is fed to each indexer. We have made so far many optimizations to different parts of the system. Data is ingested in near real time, and auto-scaling of the ingestion components works smoothly. But still, users have to wait a lot of if they do a big search. So let's take a look of how we can fix that. In our current design, in order to speed up the search, the only thing we can do is speed up the execution of search queries. But these same queries are executed over a ton of data. That takes time to process, and we cannot avoid that in a way. So we have to look at the other side of the processing logic, and that is the search API. So we decide here to go for asynchronous client-server communication. That means the client sends a request to search API to create a search and instantly receives back an identifier of that search. Later on, the client can do more requests to poll for results based on that identifier. Asynchronous communication in that way has many advantages in similar use cases. Probably the most important one is the execution of program logic is not being blocked. And since threads in Search API don't have to wait for all the results to be ready, we gain a lot of performance improvements here. Or we keep the performance with less resources. Another advantage of asynchronous communication is that we have avoided timeouts when the program logic is long running. In our case, that results in better user experience, but in a different use case, it may very well minimize circuit breaking, for example. And maybe a more subtle advantage here is that search queries are uniquely identifiable, which gives us more flexibility and to the clients. So for an example, the results can be fetched many times and a search can be canceled and so on. Now that user experience is somewhat better, but the client will be able to fetch results not until all searchers have provided results. At this point, it is much more efficient to serve results as soon as they're ready and not to wait for the whole search to complete. Therefore, we need an intermediary component that accumulates search results. Here we introduce the aggregation component. So that component sits somewhere in between of the search API and the searcher. And besides aggregating results together for a single search, it makes them retrievable as soon as they are provided by the searchers. And this way, the client can start working with some partial search results before the whole search completes. All right, now let's do a recap of what we went through in this presentation. We started simple with just a server and a client. We went through common design patterns for performance like scaling, asynchronous processing, partitioning, and messaging. We continued evolving our example by adding a real-life problem to it. We then applied those best design practices to our case in the context of various business requirements. And we ended up with a very simplified version, but a battle-proven architecture for high performance. Now, the 3 takeaways for high performance I'd like you to remember from these presentations are to use some kind of messaging, to be eventually consistent, and to go for async communication whenever possible. Thank you for your time. Hope it was helpful, and don't forget to take your survey. Take care.